In the previous module, we have seen how a continuous time signal can be reconstructed from the samples that are represented by a set of impulses, set of scaled and shifted impulses. Now, many times it is advantageous to process the continuous time signal by discrete time systems. For example, my voice, although naturally it is continuous in time, let's say if I want to improve my quality of voice, or let's suppose I need to remove the noise from my voice, or I want to enhance my voice or do any such operations on my voice signal, it would be advantageous to convert the continuous time signal, that is my voice, to a discrete time signal. That means a sequence of samples that actually represents my voice. What I mean to say is that although a signal that is available naturally is a continuous time, so let that be x of t, let that be my voice signal. Although it is a continuous variable, this t is a continuous variable, it is advantageous to convert this voice signal to a discrete signal. Let's suppose if I want to save the voice in my computer, so this continuous time signal cannot be saved in the computer. We need to discretize this continuous time signal, or in order to process also, this signal has to be discretized so that we can then apply it to any system that can enhance or improve the quality of the signal if we want to do that. So what we have seen so far is we have taken the continuous time signal x of t, and in order for extracting the samples out of this signal, we have multiplied this x of t with p of t. So we have multiplied this signal with p of t, that means the train of impulses. We have multiplied these two signals, so I have taken x of t, I have taken p of t, and I have simply multiplied them together. In order to obtain a new signal, that is xp of t, and we have seen these steps in the previous lecture. In the previous lectures, you can see that this is the underlined signal, underlined continuous time signal, and let's suppose if we want to discretize it, we need to have a train of impulses p of t, and if we multiply these two signals, we are going to have xp of t, that is again a continuous time signal. However, it is going to be the scaled and the shifted version of these impulses, and the corresponding Fourier transforms are shown on the right. So this is the Fourier transform of the original signal, this is the Fourier transform of the train of the impulses, and this is the Fourier transform of the sampled version or xp of t. You can see that this Fourier transform gets replicated at every integer multiple of sampling frequency. Now the point to note here is that the resultant signal that we have obtained here, xp of t, we can recover back the original signal x of t by imposing the two conditions of sampling theorem that we have seen in the last module. We said that we can recover back the original signal if we have the low pass filter, or you can have the filter such that the cutoff frequency should retain this middle replica and should ignore the rest, and the sampling frequency must be twice of the maximum frequency, at least the twice of the maximum frequency that is present in the signal. Now you can note that xp of t is still continuous in nature. Just because it's a function of t, it is still continuous in nature. So we can't feed this to a computer. This signal is still continuous, and in order to discretize this, we need to convert or map these impulses into sequence. What I mean to say is that this xp of t is still continuous, and therefore we need to convert this xp of t So the signal that we have just obtained is xp of t, that is still continuous in nature, and we need to convert or map this set of impulses to the sequence. So that is done by using the continuous time to discrete time converter, or the impulse train to discrete time sequence converter. So let's suppose I'm having a box here. So I'm given the signal to, let's say, so this is the continuous time to discrete time converter. Or I'll write that as the impulse train to, write that as impulse to discrete sequence. This is the converter. What does converter do? It simply takes this continuous time signal, that is xp of t, and it will extract this xnt, that means the value of the signal at these locations, and save those values. That means at the end you are going to have the signal something like this. You'll only have the sequence or the sample values at those locations. So you may see the difference between this signal and this signal. This is simply the sequence, that means the values that are present at those locations of the signal. So this is the discrete time sequence that we need to obtain in order to feed it to a computer. So let's suppose I'm having a device that actually converts these impulses. Which impulses? The train of impulses that we have obtained, that is xp of t, and should give you a discrete sequence, the sequence in these terms. So this discrete sequence is nothing but x of nt, and a shorthand notation will indicate that with x of n, just because now it is function of not t, but it is a function of the discrete variable, that is n. So, and this is a function, this is the function of n, that is the number, that is an integer. This is the discrete sequence that we would like to obtain, so that we can give it to a computer for, let's say, for saving the signal, or let's say for processing the signal, and so on. So at the output we may expect the signal as we have drawn it here. So at the output we may expect a signal that is x of n. What is x of n? X of n is simply x of nt being discretized. So this x of n. So assume that we have that device that can retain only the amplitudes, that is xnt, the amplitudes or the values of the signals at those locations, and save them one after the other like this. So these are the amplitudes of those signal at those locations and being saved one after the other, so we get a kind of sequence. Now let's see what is happening in the Fourier domain. This being a continuous time signal, it is having the Fourier domain representation as something like this. What is xp of t? Now let's try to write the expression for xp of t. The xp of t is simply the multiplication of x of t with p of t. So the Fourier domain representation of xp of t, that is xp of omega, is going to be, we have seen that already, the xp of omega is simply, so let me write the time domain expression first. The xp of t is simply x of t times p of t, and this is equals to, see that this is equals to summation this n going from minus infinite to infinite x of nt del of t minus nt. Why is that? Because p of t is the train of impulses. These are the train of impulses, and after multiplying them together, we are going to get the expression something like this. We have seen this already. Now let's try to find the Fourier transform of this. So see that this is x of nt and this is del of t minus nt. So we know what is going to be, now this x of nt is a scalar, so it's simply a value. And what is this? This is a function of t. Of course, it is being shifted by integer multiple of capital T, that is the sampling duration. So this is going to be equals to, so xp of omega, that means the Fourier transform is going to be, so just because x of nt would be a scalar that can be taken outside, and this one here del of t is having the Fourier transform as 1, and the shifted version of del is going to have the Fourier transform as the exponential to the power minus j omega and t. And yes, that factor, the scaling factor of x and t will be there, so this is going to be, so let me write that once again. This is x p of omega is going to be, as we know, the Fourier transform of del is 1 and the shifted version of del is the exponential, so this exponential is e power minus j omega and t times 1, so, and the scaling factor x and t would be there. So this n running from minus infinite to infinite, and we know what is this x and t. This x of nt is nothing but this x of n, so this is nothing but x of nt. So what we have done here is that this x of t multiplied by p of t is going to give you xp of t, that is a continuous time signal, and in order to obtain the sequence, we must retain the values of that signal as those locations, the sampling locations, and after retaining the values, those values are x of nt, we are simply indicating that with x of n. And if we do that, the expression that is xp of t here, xp of t at this point here is going to have the Fourier domain representation as xp of omega, and simply by using the property of the Fourier transform we obtain this expression xp of omega. Now this is, as I have said, xp of t is still a continuous time signal, And now if I apply the impulse to discrete time converter in order to obtain, or in order to retain only x of nt, just because this is a discrete sequence, I can always represent that using discrete time Fourier transform. So let me first emphasize this. So what is this? This is the Fourier transform of xp of t, which is still continuous in nature. So let me write that this is still continuous. This is still continuous. And so this is still continuous, and this one here is discrete in nature. Now this discrete signal can always be represented using discrete time Fourier transform. So let me write that the discrete time Fourier transform is given by, so x, the discrete time Fourier transform, so x of omega is given by summation and running from minus infinite to infinite x of n e power minus j omega n. Now this is the expression of discrete time Fourier transform. That means for the signal that we would obtain after discretization, and this is the Fourier transform of the continuous time signal just before the conversion. So let's observe a close relationship between this xp of t and x of n in the Fourier domain. So xp of omega, you can see that it is summation and from minus infinite to infinite x of nt e power minus j omega nt, whereas this x of omega is summation n tends to minus infinite to infinite x of n e power minus j omega n. If we compare both of this, you can see that if we compare both of this, you may see a close relationship between the continuous frequency variable and the discrete frequency variable. The relationship is that this omega and t, this omega and t here is in fact equals to this small omega. What I mean by that is this omega times capital T is equals to small omega. Now that is the close relationship between the continuous frequency and the discrete frequency variable. What is capital omega? The capital omega is the frequency of continuous time sinusoid, and this is the small omega is the frequency of discrete time sinusoid. So this relationship actually indicates the scaling factor of capital T with the continuous frequency variable in order to obtain the discrete frequency variable. That means if I'm having the Fourier representation of this continuous signal xp of omega, then if we wish to see the frequency domain picture of its discrete equivalent, then you have to simply scale this omega by t. That means these samples are obtained from the continuous time signal x of t. You can see that this impulses, that means the impulses of xp of t, if we retain only the amplitudes or the values of this signal at these locations, we would obtain this discrete time signal, that is x of n. So we now have found a relationship between this xp of t, the Fourier transform of xp of t, that is xp of omega, and the Fourier transform of this signal x of n. And that relationship is this: omega t equals to small omega. What it means is the Fourier representation of this discrete signal or discrete sequence is going to be same as that of this one, of the continuous signal. The only change is going to be in the scaling factor. That scaling factor is this capital T. So let me write that once again. So what I mean by that is this signal is actually obtained from this signal here, so let me write that on a single page. So this signal x of n t or x of n is actually obtained from this signal by retaining only the amplitude values, and this process is, as we have called, is as this impulse to discrete sequence converter. Now we are going to see what is going to be the case for the Fourier domain. The Fourier domain representation of this xp of omega is this one. So let me copy that and paste it here. So this is the Fourier domain representation of xp of t, that is being indicated by xp of omega. Now, as we know the relationship between the omega variable and the small omega variable, we have just derived the relationship, that is omega t equals to small omega. The Fourier domain of this x of n is going to be the same, or we would say a similar kind of Fourier domain representation we would obtain for x of n, merely with a scaling factor. So it is going to be the same representation, a similar kind of representation, but the only change would be the scaling factor. So each of this omega, the omega axis, is going to be scaled. So this representation will be for now capital X of omega, small omega. So what would be the change? The change would be simply whole horizontal axis will be scaled by a factor of t. So everything will be multiplied by t, capital T. In order to obtain the axis that is small omega. So now for this discrete time signal x of n, we would obtain the axis as small omega. Now let me simplify this. This omega s is actually 2 pi into fs, that means 2 pi by ts, and that t and this t will get cancelled in order to give 2 pi. So what I mean by that is this thing is equals to 2 pi, this is equals to 4 pi, this is minus 2 pi, this is minus 4 pi, and so on. Why? Because this omega s is 2 pi by t, and just because we are scaling that with a factor of capital T, it is going to be 2 pi. So now this axis is omega axis. So let's quickly recap of, let's quickly see what we have seen so far. We were having this x of t, and we said that it is advantageous to convert this x of t to a discrete sequence. So the first step of that is to multiply this x of t with a sequence of impulses, with a series of impulses. So we have multiplied that with p of t. This p of t is simply this impulses, a train of impulses. After multiplication we got xp of t, that is still a continuous signal, that looks something like this. It is simply the scaled version of this train of impulses. And the resultant Fourier is going to be the replicated version of the Fourier transform of the original signal. Now this signal being still continuous, we have to do some more processing in order to discretize this. That means we have to convert these impulses or map these impulses to discrete sequence. So we just have to retain the values here and save it. So those values are saved like this. We simply retain the values. So that process is done here when we convert these impulses to discrete sequence. So we simply retain the magnitude, the values, and arrange them one after the other in order to obtain x of n that is equals to x of nt, or the values of the signal at those locations. Now this being a discrete signal, we have obtained a relationship between xp of t and x of n in Fourier domain. The Fourier transform of xp of t is calculated like this. So xp of t is x of t times p of t, that is x of nt times del of t minus nt, just because p of t is a train of impulse, I have represented like that. And x of t being multiplied, it will simply extract the value at that location. And by using the Fourier properties, we would obtain the expression as summation x of nt power j omega nt. This expression is then compared with the expression of the Fourier transform of a typical discrete time sequence. So the Fourier transform of a typical discrete time sequence is given by this: x of omega equals to summation and from minus infinite to infinite x of n e power minus j omega n. And if we compare these two expressions, we can see that this capital omega is related with small omega with this relationship. What is capital omega? Capital omega is the frequency of continuous time sinusoid, whereas the small omega is the frequency of discrete time sinusoid. And we find the close relationship between these two. So the Fourier transform of this signal, discrete sequence, is going to be similar to the Fourier transform of xp of t. The only change is going to be in the scaling factor of t. So that is actually captured in this expression. The Fourier transform of the discrete time sequence is going to be similar to the Fourier transform of the continuous time sequence. The scaling factor is going to be capital T. So wherever you find omega, you just have to multiply that with t, capital T. So that's what we have done here. The xp of t are the train of impulses, which is having the Fourier transform like this. If you want to retain the sample values, we simply have to scale the axis by t in order to obtain this 2 pi at the locations of omega s. Now we will be dealing with this kind of graphs in future. So this omega s in continuous frequency, in the frequency of continuous time signal, is actually reflected as 2 pi for the discrete time signals. So if omega s is equivalent to 2 pi in discrete time signals. We shall see more into this in the next module.